Hello everyone, my name is Berto Ramazani, and this is a presentation of my project for the course Pattern Recognition and Intelligent Systems at the University of Florida in spring 2020. The title of my project is Handwritten Character Recognition using various machine learning methods. So we first we want to see the problem that we want to solve in this project. Humans can easily understand any text file in any context, and recently artificial intelligence has tried to improve the capabilities of machines to do the same task with minimal error. And they have achieved very good results in different contexts. For example, to detect the tags of cars, to detect the text on different boxes, and also the handwritten um, uh, files from humans. But in this project, we're focusing on single character recognition, and the character can be either digit or lowercase or uppercase letter. Uh, Various methods are developed to detect and classify the handwritten characters, but neural networks have shown promising results with minimal error. And here, for example, we can see uh, an example of a fully connected feed-forward neural network, which is given with a handwritten letter or word, and then it can easily recognize all of the letters. The dataset that we are using in this project is the MNIST dataset, and it actually has 6 different classes, but we have just used 3 of them: the by class, letters, and digits. The by class has the by class part has 62 classes, digits plus lowercase and uppercase letters, and it has the maximum number of elements for both training and tests compared to the other 2 classes of datasets. The letters class of the dataset has 26 classes of lowercase and uppercase, and the last one is the digits, which is from 0 to 1, and the number of elements in training set and test set are shown in this table. And here we can see a sample from the by class dataset. It has both uppercase, lowercase, and also numbers. Here we can also see the frequency of elements classes in these 3 datasets. The by class dataset is not balanced, which means that we have more samples for the digits compared to letters, but the letters and digits classes are completely balanced, and we have same number of samples for all of the classes. We have used 2 different models in this project to classify and detect the letters and also digits. The first one is a 2-layer feed-forward fully connected neural network. The input layer has 784 neurons. And the reason is that all of the images in this dataset is actually 28 by 28 pixels, which means that we need to have 784 neurons in the input layer. And then we have a first hidden layer of 1000 neurons, and then it is followed by a hidden layer with the second hidden layer with 500 neurons. And the output layer, the number of neurons in the output layer depends on the class of the dataset that we are using. For digits it has 10, for letters it has 26, and for by class it has 62. The activation function that we're using for model 1 and also model 2 is ReLU, and the learning rate is 0.01 for both models. The second model is actually a convolutional neural network. We have 2 steps of convolution step and also pooling. which is then followed by a two-layer neural feed-forward fully connected neural network to do the classification. For the first part, which is actually the feature learning, the filter size for both of these two convolution steps is 5 by 5, and it is followed by a pooling step that tries to decrease the computation time, and the kernel size for pooling is 2, and also the stride is also set to 2 for both of these layers. And at the end of the convolution part, the data is flattened to give a vector to the feed-forward neural network part to do the classification. And the same case, we have the same case here for the output layer, and the number of neurons here in that layer depends on the class of the dataset that we are using. We have applied these two models to different classes of the dataset. The first class is of the dataset is the digits part, and here we can see a sample of the data that we have in this dataset, part of the dataset. Here on the left side we can see the loss plot for different training batches, actually for different training batches of the data that are fed to the network, and the network is trained with that. So we can see that the loss of training is almost similar for both of the models. It is not very different. Actually, the model 2 is slightly better, but the difference is not very considerable. But when we compare the accuracy of these two models, it is clear that on the test set, it is clear that the model 2 performs slightly better compared to model 1. And here we can also compare the confusion matrices of these two models, and it is the model 2 performs real good. We don't have many classes that are assigned by mistake, but here we can see that the model has a hard time to recognize 0 and 8 and 4 and 9, which are almost a little bit similar to each other. So the next class of dataset is letters, and we have applied both models to this class of the dataset. And first, the training loss is compared for model 1 and model 2. We can see that model 2, the cross entropy loss is slightly lower than 2, but for model 1 it is higher than 2. And we have also compared the accuracy of these two models, and it is clear that model 2 has outperformed model 1, and the difference between the performance of these two models is more visible compared to the digit dataset. And finally, we have compared the confusion matrices of these two models. We can see that L and I, and also G and Q, which are almost similar. Both of the models have difficult time to recognize these two classes successfully. But in model 1, we can see that there are more classes of data which are assigned by mistake, and it is clear that convolutional neural network is a better tool for classification and detection of images. And the last but not the least dataset that we have used and applied these two models to the data is the Y-class dataset, which has both uppercase and lowercase letters, and also the digits. Here we can compare the training loss of these two models, and here it is completely clear that model 1 has larger loss compared to model 2. And also we have compare the accuracy of these two models. And we can see that from digits to letters and then by class, the accuracy of the model, both of the models are decreasing, and the reason is that we are adding classes that are more similar to each other, and both of the models cannot detect and classify these samples without having any knowledge about the context of the letters, since they are very similar. For example, L and I. And here we can see the confusion matrices of these two models for the by-class dataset. We can see that model 2 has done a good job, except for some of the classes which are assigned mistakenly. For example, here we can see that m, lowercase m, and uppercase m, which are very similar to each other. We can see an error here, or for example for L and 1. And as I mentioned, it is really difficult for these two models to, for any model actually, to detect these, detect and classify these images without having any context, any knowledge about the context. But for model 1, we can see that the model has just has performed well for the digits, but not for the letters. And the reason is that in the by-class dataset we have a lot more data and samples for the digits compared to the letters. And this model has tried to learn the digits better compared to letters, and that is why it has performed very good for digits, but not we don't see the same performance for the letters. So now we go to the Python code and we run for example the convolutional neural network part for the digits dataset, which is the fastest one actually, since we have less number of classes. So we first initialize the parameters, and then we load the data, and here we show a sample of the data, 6 different images. Here is the model that we use for the convolutional neural network. As I mentioned, we have 2 different layers of convolution layers, and the filter size is 5 for both of these, and then it is followed by a dropout regularization to prevent overfitting and also decrease the computation time. And then we have 2 different two hidden layers with different sizes. And here we can see in the forward pass part that we do the convolution, then pooling, and then we use the ReLU activation function. And then here we flatten the data, we apply the first layer, the hidden layer, then we again perform dropout, and then we use the third hidden layer. We don't use softmax here since we are using cross entropy, and softmax is actually automatically incorporated into cross entropy. Then we initialize the training and test parts, and here we can see that for the optimizer we are using Adam optimizer with the learning grade, which is set here to 0.01, and the loss function is also the cross entropy. So now I run the code, and since it takes some time to do the training, I just skip this part. But here you can see that the code is started.